Hello class, today we're going to talk about series circuits. Now I know a lot of you may have heard this term before, either in a Principles of Engineering classes or some other physical science or physics class. So bear with me, but we're going to be doing some calculations. This is going to be a reminder for some of you, new content for some of you, but in general it's not very difficult. Because when things are in series, all we have to do is add them together. But first we're going to define what it means to be in series. What we see on the right of the screen right now is an example of a series circuit. So in circuitry, being in series just means in a row. So if we are tracing this from the rightmost battery, right here, the rightmost cell of the battery, we see we have one battery that then leads into another cell of a battery that leads into another cell of a battery, that then these come around the corner, and because there's nothing on this wire here, there's nothing that happens, then there's a resistor and another resistor. So these are 3 voltage sources in series and 2 resistors in series. Now, if we compare that to what we have on the left, this is what's called a parallel circuit. Because you can see that if we just follow this, we don't run into our other voltage source if we just follow it straight around. So there's multiple pathways that we can choose between, and that's how we call it parallel. So this on the left is not a series circuit, only on the right is what we have as a series circuit. We'll talk more about parallel circuits in our next lesson. Now, when we have batteries in series, as we mentioned briefly before when talking about the multi-cell battery, we just add the voltages of all of the batteries together. So in this problem that we have on the right, we have a 1 voltage, a 2 voltage, and a 3 voltage cell in series. We just add them all up. 1 plus 2 plus 3 gives us 6 volts total. So this whole battery of 3 cells gives us 6 volts of voltage. Now we have to be careful which direction our voltage sources are pointing. If we look at the example on the left, our 1 voltage source is pointing to the left. Our 2 voltage source, however, is pointing to the right, and then our 3 voltage source is also pointing to the left. So we have to pay attention to which direction we have our long part and our short part, because remember, the voltage source pushes current in the direction that the long part of the voltage source is. So in order to figure out what the total voltage here is, we're going to have to take 1 volt minus 2 plus 3 to end up with a final voltage of 2 volts, because we have some voltage pushing one direction and some voltage pushing the other direction. Resistors in series are going to look something like this. Now, resistors in series are actually even more simple than voltages in series, because with resistors, we don't have to care about the directionality. The resistance is just going to resist motion. It's kind of like when we talked about gravity before. If you have charge flowing from left to right, then the resistance is going to resist the motion of that charge. If you have charge flowing from right to left, again, the resistance is going to resist that charge. So it doesn't make a difference the direction. Resistors work in both directions. To figure out the total resistance of this circuit, we would take 20 plus 30 plus 40 to give us 90. How about 90 ohms? The really nice thing about series circuits is that the amount of current flowing through one portion of the circuit is going to be the same as the amount of current flowing through another portion. This property derives itself from the conservation of charge property that we've talked about in the previous chapter. Because if we have charge coming out of our batteries and there's so much charge flowing around this corner in a second, that would be our current. That amount of charge flowing around this corner has to be the same amount of charge flowing around this corner, because we have to have that charge conserved, and we're not going to have a buildup of charge. We're not going to have like 80 coulombs of charge just hanging out here, so a bunch of charge is coming around this corner, hanging out here, and then not moving on. So when we have things in series, the current throughout the whole circuit is going to be always the same. To evaluate the circuit, first we find the total resistance, R tot, is equal to the two resistances in series to give us 60 ohms. And we have to calculate our total voltage. 1.5 plus 1.5 gives us 3 volts. Then we plug this into Ohm's law. V equals IR. Plug in the numbers we have. 3 equals current times 60. Divide both sides by 60, and we end up with our final current of 0.5 amps. Now that means that at this point here, and at this point here, and at this point here, and at every point on this circuit, we have a current of 0.5 amps. Now when we're talking about circuits in series, we can also look at where the voltage is at any point along the circuit. So we have 4 points here. We have point A, point B, point C, and point D. So each of those is on the circuit. So point A is here right after our 2 batteries. Point B is in between our 2 resistors. C is after our 2 resistors. And D is between the 2 batteries. Now when we're doing this, we have to have our first step be finding the current through the whole circuit. But because this is the same circuit that we used before, we already know that the current is 0.05 amps. To start off with, we need to figure out what our starting voltage is. Our starting voltage is going to be our voltage at point A. Now, because we have 2.5 voltage sources, we start with our total voltage of 3 volts. Then we have to figure out what's going to be the voltage drop across our next resistor. Our voltage drop for an individual component, we can still use Ohm's law. We just have to isolate it to that individual component. So across this resistor, our current is going to be 0.05 because it's the same everywhere. And our resistance is going to be our 20 ohms. One thing to notice is that we've been calculating the delta VB, because I said the drop across this resistor. So we can actually figure out the absolute value at B by taking our voltage at A and subtracting our delta VB. So we take our 3 volts at VA minus our change in voltage across this resistor to give us 2 volts at point B. So to solve the next part of the circuit, we need to figure out what the voltage drop is across this 40 ohm resistor, what we're going to call delta VC. Remember, V equals IR, so delta VC equals IRC. Plug in what we have for our current and our resistor of our second resistor, and we end up with 0.05 times 40, which gives us a delta VC of 2 volts. So then if we plug that in to what we had before, our absolute voltage at C is going to be our voltage at B minus the change in voltage at C. And so we get VC equals VB minus delta VB, which equals 2 minus 2, which gives us 0 volts. Now, this makes a lot of sense because right now we are at the end of our circuit, right? We had our 3 volts, and then we went over one resistor and another resistor, and now we're back at the end of the circuit. One thing with these sort of circuits, you're always going to end up with 0 volts when you get back to the circuit. Now, if we want to look at what our voltage is at D, we do a similar sort of thing. We take the voltage at C, and then we add the change at VD. Because this is a 1.5 voltage battery, it gives us back voltage. And so we add this 1.5 back into our system, and we end up with 1.5 volts at this point in our circuit at D. And then if we continue a little bit further, we would do another 1.5 volt addition to get us back to A, where we had 3 volts, which was our total voltage. Now, one thing to pay attention. When we are dealing with resistors, like with C, we have a minus change in voltage because resistors cause us to drop voltage. However, battery sources is going to be an addition because changes in voltage from a battery give us back voltage when they're in the direction we're heading. So that's why we end up with a positive 1.5 after going across this battery. Now, power is going to be really easy because we've already calculated everything we need to do to calculate power. If we zoom in on that 40 ohm resistor that we had before, and we look at what our current and our voltage is, we know that the voltage drop, so our change in voltage from B to C is going to be 2 volts, and our current is going to be 0.05 amps. So we just need to plug these two parts of the equation, our current in for our current, and our voltage in for our voltage. So power equals current, which is 0.05 amps, times voltage, which is 2 volts. And we end up with 0.1 watts for our power. And you can do that for any resistor or voltage source in the battery. So if we're in the circuit. So if we're looking at a resistor, it's going to have negative work. We're going to be losing energy. So technically, this value here should be a negative value. If we have a battery, it's going to be positive work. We're going to be doing work on the system because we are getting more energy into the system. So a resistor is going to heat up, and that heat is going to be the negative work. So this is how much work is made in heat over that resistor. Okay, so here is your quiz for this lesson. First, what is the total resistance of the circuit? Oh, and just so you know, we have a circuit, 3 resistors in series, a 10 ohm, a 20 ohm, and a 30 ohm resistor, and there is a 3 volt voltage source also in series. So first, what is the total resistance of our resistor, or of our circuit? Second, what is the total current through the circuit? And third, what is the voltage drop across R2? Go ahead and fill out your quiz sheets and bring them into class, and I'll see you next class period.